Okay, so let's start with our keynote speeches. So we have two very outstanding speakers today to get all of us more up to date about the development of AI agents in scientific research. Our first speaker is Dr. Shunyu Yao from OpenAI. He's a researcher in OpenAI. He graduated from Princeton, and he's one of the pioneers of the AI agents. For example, his work on React agent is the foundation of many AI agents today, and this work has been cited more than 3,000 times in the past 2 years. So, and has many other significant works. So today we are really glad to hear his insight on the development of LLM and AI agents. The title of the talk is the second half. Okay, Shunyu, please take from here.
Cool. I was told to give a 25-minute speech, so I will make it short and I'll open some questions. So this talk is based on my recent blog post. So if you want to read more details, you can check out this blog post. The TLDR of this talk is actually very simple. I think we're at a very special time in AI's development. So far, we have been focused on training, and the goal is to make progress on a bunch of problems and benchmarks. But what makes now very different or special is that we finally have a recipe to solve problems. And the recipe is somehow general and it's based on language model and RL. So that changes the situation. And I think from now on, defining problem is going to become more important than solving problems. And so, I mean, like to look at, what has happened before now, right? If you look at all the most important work from AI, in like AlexNet, like DQN, Transformer, Backprop, GPT-3, you notice that all of the most important work is trying to solve problems by proposing a good model or like a good training method. And what's really interesting is that if you look at all the benchmarks that they evaluate on, they seem to be much less impactful. So clearly we can see that like remarkable ideas and remarkable engineering that are like accumulated from scratch, right? 6 years ago we have no AI, and today we have lots of methods, and all of those are human creations. But on the task side, everything is kind of trivial because there are so many human tasks existing, right? You have image recognition, you have exams, you have Go, you have all those games, and methods has been more general than task, therefore it's more valuable, right? If you think about transformer versus the original task is trying to solve, like the method is obviously much more general than the task. That's why it's more impactful. But I think what's really different now is that we have accumulated enough good things that we start to have a general recipe to solve problems. And what do I mean by that? So if you look at like in the past 5 years, all the benchmark, right, everything is just increasing so fast, and it's just faster and faster. And if you think about what's behind all the progress, right, really like the keywords are language, scaling, pre-training, and reasoning. And obviously those are some of the hottest words in Bay Area, but how do they really form a recipe that changes the game of AI? I think it would be easier to organize this through the view of RL. So I think people have always known that RL is very important, right? Many years ago. But we don't really know how to really do RL well until now, in some sense. It took us a lot of detours and some decades to find a working recipe for RL now. Now, like when I say a working recipe, obviously there could be other working recipe, but so far this seems to be the only like generally working recipe. And this recipe is that to make RL work, you need to have a good prior, you have to have a good environment, and you have to have a good algorithm, and you need all of them. So let's take a look at what has happened in the past decades. So by default, obviously, people think the most important thing is algorithm, right? Because algorithm is the most intellectual part, and You have so many smart methods, right? Like TD learning, actor credit, all those math and all those intellectual algorithms and analysis. So obviously, first our researchers focus on algorithm, which is the intellectual part, and then people don't really study prior that much, right? So if you look at this classical textbook of reinforcement learning by Sutton and Bartle, right, most of the chapters or all the chapters are about the method, and the task is just as minimal as possible, right? To show the power of bending method, you just look at like paper, rock, scissors, right? And there's no prior, right? You always just train a model from scratch. But empirically, environments matter, right? So all those empirical results of algorithm are highly specific to the environments. So it's really hard to talk about the usefulness of algorithm without talking about what environment you're trying to solve. So since like deep RL started to work, right, especially after 2010, people realize environment is very important. You need to have very good environment so that you can develop good algorithm and solve the right problem. So in the kind of empirical deep RL era, a very reasonable change of plan is first you create the environment that you actually care about, and then you try to find an algorithm to solve it. That way you make sure that you're trying to solve the problem that you want to solve, right? Somehow that's the initial plan of OpenAI, right? The first project of OpenAI is called Gem, and some of the initial projects include like universe and what are bits, and all the ideas are very consistent. Like, why don't we just first try to compile all digital environments we can think of, like games and computer and web, everything, into environments? Then once we have those environments, we can develop RL to solve it. Then you just solve digital AGI, right? That worked for a while, right? Like this has worked to solve Dota, and some other games, even some robotic cases, but not really for computer and web. And long language environments just don't transfer that much to other environments, which is bad. So clearly there's a bottleneck. And then something very unrelated happened, which is GPT, right? Language pre-training, which seems totally irrelevant from RL. But surprisingly, only after you have a really large pre-trained model, it's possible to start making web interaction work and start to make chat work. And that's because it turns out you need to have very general prior about language, knowledge, and common sense so that all those agentic use cases can start to work. So in some sense, prior might be the most important part of RL. It's a controversial take, but the reason I say it is because it seems like before pre-training happens, none of the kind of digital agent really work for useful cases. And then we start to use pre-trained model to solve a lot of problems, chat, web interaction, so on and so forth. But there has been there's still a mismatch between the prior and the environment, especially if the environment is very different from internet text, which is the pre-training data coming from. So say you're trying to use GPT to play an arbitrary game, right? It is still very hard because the game might be very different from internet text. Especially, like in this game, if like go to door 7 is the best action, it's very hard for the GPT to catch up on that because that's very different from the general pre-training of the internet text. So one trick actually helped a lot, which is to add what we call reasoning or chain of thought into the agent's action space. So it seems to be a very simple change, but it actually showed a lot of gain, and that's where this paper of React comes from. If you think about reasoning, right, it's a very interesting thing because you can think about anything, right? You can think about a word, you can think about a sentence, you can think about a paragraph, you can think about 10,000 random tokens. It's extremely open-ended and it's infinite, right? You can think about anything. And also, when you think about anything, or it doesn't really change the world around you, right? So of all the actions that an agent can possibly do, only thinking is special in that thinking does not immediately affect the world. It only affects the agent's internal state, and through that, change its world later. So thinking or reasoning is a very special kind of action. And once we add that into the agent's action space, it suddenly makes everything much better. And lastly, with the good language prior and with reasoning as an action space, RL just become easy. And on the left, this is like the classical DeepSeek R1 kind of curve, right? With training, you can just make AMI much higher. And on the right, we're showing this test time scaling property of the operator. But it turns out the algorithm might be the most trivial part after all, right? GRPO is actually a very simple algorithm. And it turns out once you have a very good pre-trained prior, and you have the capacity to reason, and you have obviously a very good verifiable reward, then RL is just very easy. We have like O1, O3, deep research, operator, R1, a lot of incredible inventions this year. And I think this year the agent is going to be working. And that's because we have all the right elements, prior, reasoning, and RL. So to summarize, right, so I think RL is prior plus environment plus algorithm. And throughout the decades, it seems like we have found a recipe where we use scalable language pre-training as a prior. We use language reasoning as part of the action space in the environment. And we have a simple scalable algorithm. And that forms a working recipe that's not solving increasingly more benchmarks. Now, this is obviously one of the possible working recipe, but that seems to be the only general and working recipe so far. And it's obviously very hard to connect the dots looking forward, right? Like 10 years ago, no one would ever think that's going to be the way people do RL, but looking back, everything makes sense. So I think now that we have a general recipe, what will be the implementation? And I think the natural implementation is that problem solving will become more standardized and industrialized, and evaluation is going to be more important, right? So previously, training is very hard. You have to come up with all the smart ideas to make improvements on each task, and eval is trivial. But now, making improvement on benchmark is more standardized, or you can even say industrialized, and making tasks is becoming more challenging. I mean, first, it's very hard to make challenging eval because it's very hard to predict what's going to be hard, right? Or what's going to be hard today might be very easy a year from now. And I'm going to skip this part, and I want to talk about the challenge of making useful eval. So I think the general idea is that when things are not working, right? When we don't have a general recipe, there's actually much more freedom in choosing what you use for evaluation. You can use a video game, you can use a GRE exam, you can use image recognition, you can use whatever you want, right? As long as it's reasonable and you show progress. So in other words, when the intelligence was low, right, increasing whatever benchmark makes sense because they were aligned with increasing utility. Because now we have the general recipe, it really requires some reflection, right? Because now we have AI with PhD level math and science knowledge and reasoning, according to benchmarks like AMI. We have coding ability that can that's IOI gold medal level, right? And on code forces where we can be like number 50 out of the whole world population, right? There are only 50 people that's doing code force better than this AI. And obviously, they're much more intelligent than 99.99% of human on most exams, right? And still, they're much less useful than most humans on most tasks. This is very interesting, right? And I think right now, probably the most important problem in AI is what I call the utility question, which is why those AI has been so smart on benchmarks, but they're still not as useful. And I really think it's really mostly about evaluation, not training. Uh, and instead of extrapolating existing setups, we need to pursue new setups. So I want to skip this part because it's less relevant than today. But the message that I want to convey here is that uh, if we want to solve this utility question, it doesn't really take, like, it's not enough to just make a harder exam, right? So previously we have GRE to evaluate ages. Now we can try to use bar exam to evaluate ages, and then we can try to come up with a harder exam to evaluate ages. I don't think that's enough because apparently with the general recipe, solving exam is easy, right? Because it's a very standardized RL problem and you can just solve it. I think what's really interesting is to think about the difference of being a very good student with very good GPA versus being a good scientist. I think what makes becoming a good scientist really hard is obviously there's still a reward, right? Once you have made a discovery, you publish a paper, right? You prove Riemann hypothesis. Obviously, you get a reward, but that's extremely sparse compared to solving exams. And in some sense, you it's not enough to use the general recipe to become a great scientist because the reward is too sparse. So I think to solve the utility question or to make AI more useful or to solve the evaluation problem, whatever you call it, we not only need to make harder evals or different evals, we actually need to make different eval setups, right? So we need to think about what are the differences between today's eval setups and what's actually useful in real world, right? So in evals, agents always has to be autonomous without human in the loop, but that's not true for most of the tasks in everyday life. In like eval, most tasks are IID and evaluated in parallel, but that's very not true in reality where you have a sequence of tasks and you get better throughout time. We use human preferences a lot for eval nowadays, but we know it's easily hackable. We use success rate a lot, but is that really what we care about in real life? I think there are so many things we can question, right? And I think if you want to take one thing away from this talk, I think it's this, right? Eval tasks are different from real world tasks, and it's becoming more noticeable. But eval setups are so different from real world setups. We rarely think about this, and that's mostly because of inertia, right? Because those setups has been always been like this, right? So, for example, like we have been taken for granted that task has to be IID, but that was developed like 60 years ago. And without those assumptions, it's impossible to make any theoretic or empirical progresses, right? There's no way to make theory learning work, etc. So you have to assume IID. But today, do we still need to assume IID? I don't think so. And in some sense, the working recipe is developed for the standard setups that we have developed. And as long as we don't break those setups, the working recipe will just work. So if we want to make new research paradigm shift, then we have to think about how to change the eval setups. And so I think to summarize, we're living in a world with one standard recipe. And under this standard recipe, creating tasks is very challenging, but it's also very rewarding. Because if you can create very useful tasks, right, like to solve science, to solve finance, to solve a lot of the real world things, you can make great products, you can make great utility, you can help solve the utility question, and you can make a lot of money. You can also try to break the task setups or create new task setups. And that requires to break the recipe and then change the game and need to new paradigm shift. So yeah, so I think that's the end of the talk. Happy to take some questions.
Yeah, thanks, Shunyu, very much. Well, I think the utility problem you named is really exactly the problem we are trying to solve here in this hackathon in the areas of scientific research. So anyone who has questions, you can just push the space bar so you can got yourself temporarily unmuted. Okay, maybe I will start. I'm curious about the part you skipped. I see quickly that you mentioned that the long-term memory is related to evaluation. Can you say a few words about that?
Yeah, I think it's very related to the IID problem that I mentioned. So obviously, I think nowadays everybody or a lot of people are talking about long-term memory, where the idea is the agent should be able to remember some knowledge based on previous task and then use that to solve like follow-up task. And ChatGPT memory is like an example of long-term memory where you try to remember things from the previous conversation and then you try to use it for future conversations. But I really think maybe the bottleneck is not even in the methodology part, it's actually in the eval part. Because today, not all the benchmarks are assuming IID setup. And in those setups, it's impossible to prove or to evaluate long-term memory and show it's actually useful. So I think the first step to solve the long-term memory problem is not even to come up with a fancier methodology, but to actually create a task that is not IID, where if you solve previous things, you're supposed to be much better on future things, and explicitly evaluate things not in an IID setup, and then show, long-term memory is needed to solve this thing, and that will motivate better methodology to be invented.
I see. Thanks. Any other questions?
So does your talk about RL actually? So you were talking about creating RL in different environments, and then obviously today is about agents. Obviously when we make agents with MCP protocol, they don't actually do reinforcement learning on whatever the task have them doing is. Is OpenAI? I mean, once people make these agents, is OpenAI taking them as examples of use cases and trying to do RL on them, or does what we're doing today connect with what you talked about at all?
Yeah, that's a great question. And I think some of the skipped part of my talk can answer that. So it's also in the blog post. So I think first, what's really different about today's RL versus 5 year or 10 years ago's RL is that it actually generalizes because of reasoning. So obviously, OpenAI cannot possibly train on all the APIs in the world, right? But you can train with RL and reasoning to use some tools, and that can generalize to using new APIs or the new MCPs that you're talking about. And that's something very hard to think about 5 years ago, right? Because you train on one video game, you cannot possibly generalize to another video game. So clearly, reasoning makes RL generalize much better. I'm not saying generalization is soft, but it's much better now. And secondly, I think we're starting to see this kind of ecosystem, right? So obviously, the big model companies are training RL with some task to make the model better, and then people use it maybe for some other task. I think the obvious way to obtain some feedback loop is, people realize some tasks might be not working that much, and maybe not working that well, and then the model companies can start to create some proxy tasks that's more similar to that distribution of things. Like for example, if we find out that scientific API is very hard to use with today's model, then maybe OpenAI will try to create some tasks with some kind of science API and try to generalize and cover those aspects. But I really think a very interesting yet open question is, how can we bridge the gap in a better way, right? How can we, fundamentally today, training and testing is still separated. Like model companies use some training tasks to train the model, and then you're deployed to test on some other things. Fundamentally, can there be a way where we can more easily use the testing to improve training? I think that's a very important open question to be solved.
Thanks. Any last question? Okay, if not, thanks, Shunyu, again. Thanks very much.